Hi everyone. So it's a great pleasure to be here. And I guess what I'll be talking about might not be as exciting as the robot that you can see later tonight, but in any case, I'll tell you about some interesting things. And it's going to be both a bit of theory, a bit of practice, probably somewhere in the middle, but feel free to ask me questions as we go through the material. Okay, so first, let me say a little bit more about myself. So I spent half of my time as a principal researcher at Bas AI. So Bas AI happens to be a research institute that is funded by Royal Bank of Canada. And then we have 5 research centers. So there is one right here in Edmonton, but we also have some in Montreal, Toronto, Waterloo, and Vancouver. And what do? We do research that we do in a form of an integrated model. So we start from business problems, but then we also do some fundamental research. We also publish, and then we work on exciting things that lead to products at the end. So that includes some machine learning, reinforcement learning, natural language processing, computer vision, private AI, and naturally fintech, since we're funded by a bank. So in any case, if some of you are interested, feel free to talk to me afterwards. So we are hiring, and again, we have a research center right here in Edmonton. Okay, the other half of my time, I'm also a professor at the University of Waterloo. So I work on a number of things. So today I'll be talking mostly about reinforcement learning, but if some of you are interested in other topics, I thought I'd list them here. So I do some work, generally speaking, in deep learning that includes those subtopics. Today we'll talk about reinforcement learning, mostly about some of the fundamentals, some of the basics, but then if you're interested in some of the cutting edge topics, I've listed some of those that I'm currently working on with some of my students. I also do some work in natural language processing and also in theory. So any of those topics that you might be interested, I'll be happy to chat more about this. Okay, so let's get right into the meat of the topic for this session. So okay, we have a summer school that's about deep learning and also reinforcement learning. So naturally, let's start with showing perhaps what is hopefully a familiar picture to all of you. So for reinforcement learning, we have an agent. It will select some actions that influences the environment, and then based on that, there's some rewards and also a state that will inform the agent about how well it's doing. Okay, so this is our usual picture, but now for this session, we're going to make one important change. So here, we're not going to assume that we know the state or that the state is observable. Okay, so what we're going to do is relax this and essentially get the agent to work with only observations that are correlated with the underlying state. And so this is a fundamental issue that actually arises in a lot of problems. In fact, we could argue that pretty much all problems are partially observable. And then a lot of the algorithms that are typically used in reinforcement learning simply brush over this issue. But today, in this session, we're going to dig deeper into what we can do to really take into account the fact that states are not directly observable most of the time. Okay, so here's the outline for my presentation. So I'm first going to start by talking about inference. So in partially observable domains, if we don't know what the state of the environment is, what can we do to infer perhaps some distribution over what might be the underlying states? So we'll talk about hidden Markov models, but also recurrent neural networks. Then after this, we're going to get into decision making. So I'll explain how we can also come up with a policy or value function while only knowing about observations that are correlated with states, but not the states directly. So this will lead to partially observable reinforcement learning. Okay, and then the last topic that I think is pretty exciting is that when we explicitly account for partial observability, it actually gives us a way to deal with the exploration-exploitation trade-off in reinforcement learning in a very natural way, in fact, in a principled way that will lead to Bayesian reinforcement learning. So I'll explain how we can leverage partial observability for that purpose. Okay, so let's get started with the first topic, which is inference. So in reinforcement learning, we typically assume that we have a process where the environment evolves over time, and then we have some states that correspond to random variables that change at every time steps. Okay, so the classic assumptions are that we assume that our process is Markovian, which means that the next state will typically depend on the entire history of the entire history of the process. But if it's really Markovian, then only the last state would be sufficient. Okay, so this would correspond to the first order Markovian assumption, where we in fact don't need to know about the previous states, just the last states that's sufficient. So this is a common assumption that is made. The second one is that the process is typically assumed to be stationary, which means that when I look at the distribution over the next state given the previous state, that would be the same at any time step, so it shouldn't matter where I am in the process, right? So the distribution of how the state will evolve over time does not change itself. Okay, so these are the two common assumptions that are made. But now, if we don't get to observe the states, we often need to change a little bit those assumptions and adapt them to the fact that what we are really working with are observations that are correlated. So this is where it leads naturally to a hidden Markov model. So a hidden Markov model still has those two assumptions, but now because we don't observe directly the states, what we have are going to be sensor measurements that are correlated with the states. And here too, we can make some assumptions about Markovianness and stationarity. Yes?
So I was wondering, do we really need the stationary assumption if we already have the first order Markovian? Because I feel like the first one already implicitly incorporates the stationary assumption.
Actually, no. So we do need the two assumptions. At least the first one does not imply the second one. So you see, if I have the first one, all it means is that a given state only depends on a previous state, but then I could have a different distribution at every time step, which would mean that it's still Markovian, but non-stationary. Okay? Yeah, so we do need the two assumptions, or at least to make things tractable, it is common to make those two assumptions. Okay, so once I introduce the notion of observation, so here the idea is that the state is not directly accessible, so we do not observe it directly, but instead we have perhaps some sensor measurements. We're going to see some examples in a moment. And here we can also make an assumption of that the emission process is stationary, meaning that an observation at a given time step only depends on the current state and not the previous states. Okay, so these are our typical assumptions, and then these are not necessarily difficult assumptions to satisfy because we can always change our state definition so that they get satisfied. Okay? All right, so hidden Markov models in fact became very popular many years ago in the context of speech recognition. So this was really the application that made them popular. And it was also in speech recognition that hidden Markov model led to a breakthrough in terms of using a probabilistic model to improve their recognition accuracy. Today, they're not anymore the state of the art, so it's mostly based on recurrent neural networks, but still, decades ago, this was an important breakthrough. So here, for speech recognition, the idea is that we have an audio signal. It could be in the frequency domain. We can also measure the amplitude. The idea is that you've got a signal that evolves over time. And now these are your observations, and you'd like to recognize some hidden state based on this that would correspond perhaps to a sequence of phonemes or otherwise a sequence of words. So here we can define our hidden states to be different at different levels of granularity. But okay, the most two common levels would be phonemes and also words. So now we can think of this, again, if I go back to the previous slide, where you see I've got my audio signal that corresponds to these observations. So we can take the audio signal and then extract from it some features that we would put into a frame for different time steps, and that would correspond to these observation variables. And then the state here at every time step would correspond to what we're trying to infer, so either a phoneme or a word. Okay, so yeah, so this was one of the first important applications of hidden Markov models. Okay, so now in the context of reinforcement learning, perhaps another important application would be mobile robotics. And there, too, there was an important problem many years ago. So in fact, when I was a student, one of the hard problem of mobile robotics was that you had a robot, and then you would program it to go to some location. But the problem is that the robot would get lost on its way. And at the time, we did not have good ways of ensuring that a robot can keep track of its location. So here you could think of a robot as having an odometer, and if you give it some instructions, like for instance, if it starts here, and you give it an instruction of going right by, let's say, 1 meter, and then right again by another meter, and then right, and then up, and left, 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 right? Then you could imagine that the robot should know its location simply because with the odometer it could keep track of the distance covered, but the problem is that the odometer is not precise. So here, what this illustrates is that if you give the same instructions, so right, 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 up, 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 and then left a number of times, and you repeat this experiment multiple times, then the robot will end up at slightly different locations, and the error is going to build up over time. So in this plot, you can see every point is essentially one experiment where you give this sequence of commands to the robot, and then it ends up at a slightly different location, and you can see that the error just grows over time. Okay, so this was a big problem, and then the solution for, I guess, reducing the error was to essentially treat this as an inference problem by using a hidden Markov model. Okay, so here we can formulate mobile robot localization as a hidden Markov model, where the idea is that the states would be the coordinates of the robot on the map, and then the observations could be sensor measurements, for instance, distances to surrounding obstacles that could be measured by laser rangefinder or sonar, or even today, a video camera. Okay, so you equip your robot with some sensors. It can measure distances to different objects, different obstacles, perhaps walls in the environment, and then given a map, when it detects something, then it can infer back perhaps what its location is, or at least reduce its uncertainty and rule out some of these locations. So we can formulate the problem of mobile robot localization as essentially an inference problem where we're asking what's the probability of the current location given all the past sensor measurements. Okay, so the next question is, how do we go about computing this? How do we do this inference? So here we can use various laws of probability theory to essentially arrive at the following derivation. So given a hidden Markov model, then we can start with some current estimate of the location based on past measurements, and then multiply this by the transition dynamics that indicate what's the probability of the next state given the previous state, sum out the previous state, and then also reweight these positions based on how strongly correlated they are with the observations that are made. Okay, so this equation here corresponds to the classic equation for belief monitoring in a hidden Markov model. And it's something fairly general. So here I'm showing you how we can apply it in the context of mobile robotics, but then it's the same thing for speech recognition and also activity recognition and many other applications. So any questions regarding this? Yeah?
What's the normalizer in this case?
What's the normalize?
Proportionality here, right?
Yes, okay, so yeah, so here I've got a proportional sign. This is simply because I'm applying Bayes' theorem. So there is a normalization constant that I'm not showing in this equation. And this normalization constant would essentially be the probability of the observation. So normally I would divide by that. Okay? But it's not important for the purpose of this equation. Yeah. Yes?
So you mentioned the states are the coordinates of the location of the robot. Is it a continuous variable or a discrete?
Very good point. Yeah, so here the states in the context of robot localization ideally should be continuous variables. So the xy coordinates, I mean, unless we discretize, they would naturally be continuous variables. And then so what I'm showing here is essentially a derivation where, because I've got a sum, it assumes that the states are discretized, right? And then so we won't be able to apply this directly in the context of continuous states. But then for this, yeah, let me go to this slide. There is an approximation known as particle filtering that can be used to work with continuous states as well. So the problem here is that if we have states that are continuous, then we cannot enumerate them all. We cannot represent a distribution that would be discrete with respect to the state, and instead we would have a continuous distribution, in other words, a density. The problem with this is that densities can be fairly complex, they can be quite rich, and it's not obvious how we can represent them in a tractable way. So one common approach for approximating this is to take a density and then approximate it with a set of particles. So you can think of those particles as essentially samples, but then we're going to give some weights as well to those particles to correspond more or less to how important those particles are in different regions of the density. So here I've got 1, 2, 3, 4 particles. The size indicates their weights, and I've got 3 more here. So this gives me an approximation to this density. So now what I can do is start with such an approximation, and then the first step that I would do is resample to obtain just a set of particles that are not reweighted, that are not weighted. They're just essentially a uniform set of particles. So this is just in order to make the algorithm have more diversity in terms of its particles. And then after this, we can start doing some propagation. So I have some transition dynamics that gives me what the next state should be given the past state. So then I can apply these dynamics. So for every particle, ST, then I would sample according to my distribution where the state would end up and generate a new particle. So here every arrow corresponds to essentially a sample according to the transition dynamics. Okay, so then we still need to reweight those particles based on the observations. So the next step, I cannot observe what is my next state. So I'm going to use my observation, which is a sensor measurement, and then those particles that are most consistent with that are going to get reweighted. So here you can see that perhaps these observations are more consistent with some observation OT plus 1. Therefore, I'll give them a higher weight. And now I end up with a new representation, which is an approximation to the new density. So what I've illustrated here with this picture is essentially how we can perform the same thing that I had on this slide here, this equation, but now in terms of densities that are approximated through particles. Yes?
Where do we obtain the transition dynamics from? Like, are we learning it? Where is it?
Excellent question. Yeah, so here I've only talked about inference. There's an implicit assumption that we know the transition dynamics and we know the emission distributions, but in practice, nobody gives them to us. We should estimate them from data as well. Okay, so yeah, let's continue. Okay, so in fact, I'll come back to your question. So the answer is really that we're going to learn these dynamics from data by maximum likelihood or some other technique. So I'll get to this in a moment, but let me give you as well an example of a case study, some research that I did with some colleagues at the University of Waterloo roughly 10 years ago. So this was a problem where we were working with colleagues in kinesiology, and then they wanted to know when older people are using a walker, what activity are they doing? So in other words, what action are they walking forward? Are they making a left turn, making a right turn, and so on when they're using a walker? And then the interest in inferring this was that walkers are normally supposed to prevent falls. They're supposed to help people walk more stably, but in practice, this was being questioned because there had been a lot of incidents where when people are using walkers, they might trip with their walker more easily. And in fact, at some point, I visited a long-term care facility where they were even forbidding people from using their walker because there was some danger of falling. Okay, so then, the question was, can we infer what activity people are doing at any point in time with a walker? And then this could help us understand what are the circumstances or otherwise triggers of potential falls that might result when somebody is using a walker. So we did some work, and then we modeled this essentially as a hidden Markov model. And here we're going to see that the states are the activities. The observations are sensor measurements, a bit like in robot localization, but now we're not trying to infer the location of the walker, but more what the person is doing with the walker. Okay, so in this case, we had 8 channels. These were 8 sensors that gave us measurements at 50 hertz, and we digitized them into 16 bits. So the walker that we used was instrumented in this way, so it had a camera looking backwards at the legs. There's also some modification in each leg of the walker where we inserted a load sensor that measures the downward pressure. And then we also have a wheel rotation counter and an accelerometer in the seat that tells us about 3D acceleration of the walker. So these were simple sensors, and an interesting question was then, can we infer what somebody's doing while operating the walker from that? So, okay, we conducted an experiment where we went to a long-term care facility called Winston Park. This is in Kitchener near Waterloo. And then we recruited 8 people who were residents. They were between 84 and 97 years old. And then they were all regular walker users, and we essentially asked them to go through an obstacle course with their walker. And here, just to be clear, when I say obstacle course, there was nothing dangerous, okay? What we really meant is that they had to go through a walking course where they would essentially perform traditional maneuvers with their walker. So for instance, they would go through a set of doors with a walker. They would make some turns, get into a confined space, which is the same as like going through an elevator. We also asked them to go up and down a ramp, and this is similar to going onto an inclined plane and also going up and down a curb. Let's say you're going onto a sidewalk or off a sidewalk. So, okay, so then in this walking course, the activities that we're looking for are listed here, so we wanted to recognize this. And at the time, when we were working with our colleagues in kinesiology, they were essentially asking all the residents at Winston Park to go through a similar walking course to understand better what the risk was of falling and so on. And then so they would record this, and then they would have somebody watch a video of how well the person is doing and indicate what the activity was manually. So then for us, the question was, can we automate this? Can we infer automatically what is the person doing at any point in time? Okay, so we modeled this as a hidden Markov model. In comparison to what I explained so far, the main difference is that we had multiple sensor measurements. So here I'm including 8 observation nodes that corresponds to the 8 channels. The parameters of our model include an initial state distribution, the transition probabilities, and the observation probabilities. So this is where, as was asked earlier, there's a question of how do we know what are the transition and emission probabilities. So here we have some parameters, phi, theta, and psi, that need to be learned from data. So here to learn these things from data, we simply did maximum likelihood learning. We can do it in a supervised and an unsupervised fashion. So supervised learning simply means here that we have somebody who would label the data with what is the ground truth, the actual activity that is performed at every step. And then that means we know at any point in time what is the state, so it's not hidden anymore. And then we also have the sensor measurements. And now the question is, can we find the best setting of those parameters to maximize the distribution over both S and O? Okay. Now, we can also do it in an unsupervised fashion, where if we don't have anybody label the data, then you can still learn. Obviously, the accuracy is not going to be as good, but the benefit is that it's a lot more convenient. So we can still try to infer what might be some good parameters just by maximizing the probability of the observations. So we did both. And here, okay, I don't have a slide that shows the equations for how to do supervised and unsupervised learning, but the idea is that you simply treat this as an optimization problem where you could simply write down the objective and then do automatic differentiation and then do several steps of gradient descent, essentially some form of backpropagation as would be done in any deep learning architecture, and then obtain some settings for those parameters. Okay? So the idea is that, yeah, this is the objective, and then we can simply treat this as an optimization problem. Okay, so I've got here a demo that shows how well the system performed. Okay, so what you can see in the video here is the view, a backward view from the camera that's under the seat of the walker, looking back at the legs of the person. Now, the sensor measurements that are used for inferring what is the activity that the person is doing are illustrated down here. So we've got 8 channels, so 8 sensor measurements, and then you can see the values of those sensors fluctuating as the person is going through the walking course. Now, in real time, the system needs to predict or recognize what is the activity that's being performed. So in this panel here, we've got in blue the predicted behavior, and then in red, the manually labeled behavior that we treat as the ground truth. So whenever the blue and the red square match, then it means that the system made the right inference. Whenever they don't match, then there's a mistake here. And you'll notice that mistakes tend to happen mostly when the person is changing activity, and then the timing for this is actually a little bit harder to recognize. But in any case, you can see that the system is working, and it is possible to infer what somebody is doing just based on those 8 channels. Any questions regarding this? Yes?
So your state is these activities rather than the XY.
That's right. So yeah, the states are in fact those activities here. So we have here a discrete state space that can have one of 13 values, and the 13 values are listed here. Yeah?
And the architecture for analyzing the data is some sort of recurrent neural network, I guess, right?
So actually in this case, we did this 10 years ago, okay? So recurrent neural networks were not popular yet. So we literally just use a hidden Markov model. Okay, so it was a simple architecture. It was exactly the architecture that I showed before, where I've got the hidden states and the observations. Today, yeah, we should probably use a recurrent neural network and potentially obtain better accuracy. Yeah?
These models are working with the assumption that the neural map is not.
So,
We have the states of the map. We have the states and we have the map.
so in this case, yeah, we define ourselves the states. It's just that they're not directly observable. That's what we're trying to infer. But yeah, we did come up with this list of 13 states. Yeah.
If you were to do this today, what would you change, like with all the deep
Okay, so I guess if I was going to do this today, then yes, I would probably use some form of recurrent neural network. I would also use the video camera. So back then, we did not use the video camera, so the video was essentially just for us to see as humans how well the system is doing and for manual labeling. So at the time, we were doing this simply based on the 8 sensors, but what's remarkable is that even despite this impoverished data, right, we still managed to obtain reasonable results. Yeah. Yes?
So in the previous iteration for the supervised case, so it's not a conditional density, right? It's a joint density of state and observation, which you maximize.
So I'm not sure I'm understanding your question. Can you repeat again?
So in the supervised case, just wants to make clarity. Just wants to ask this: that is it a conditional density or a joint density of state and observation?
So it's a joint density. Yeah, so here for supervised learning, we're simply maximizing the likelihood of our data that includes both the sensor measurements as well as the activities that are manually labeled. So it's a joint density.
And if you do it within RMN, then in that case it would be a conditional density, right?
Yes, so, okay, if, right, so here, yeah, we can do it. Yeah, the way we did it here was with an HMM like this, we can look at a joint density, but you're right that it might be better to use a discriminative model that essentially looks at the probability of S given O, because we're not generally interested in maximizing the probability of the observations. We've got them already, so it might be better to just maximize the probability of the states, which is what we're trying to recognize, right? So here we could obtain potentially better results by maximizing a conditional density. Yeah?
For the unsupervised case, you didn't have the state information. Did you get 13 hidden variables? Those 13 values actually look like the states you found out?
Okay, yeah, very good point. So the unsupervised case, yes, we do not know what are the states, really. So we're just giving it 13 values for the states, and then it uses them in any way it wishes. And then the idea is that after the fact, then you can look at which states tend to correspond to which activity that you're interested in. And then there is a problem here of association. So one simple heuristic is just to see, to have a look at a few of those and then essentially do a bit of a semi-supervised learning, okay? But then you also have the problem that sometimes it might use 2 states to correspond to one activity, right? So so that's not perfect. Okay, so in fact for this, let me show you some results. So here we did supervised learning. These are the top curves, and then unsupervised learning as well. You can see the accuracy. And when I show here window width, it's simply looking at measurements in the past for up to windows of size 50. So here that corresponds to 50 measurements, and that really corresponds to just 1 second. Okay, so obviously the larger the window, the better. And in general, supervised learning did perform much better than unsupervised learning, but it was still interesting to see what the results could look like. Okay, and in this slide I also have another model, the conditional random field, which did end up performing better. And part of it is because it is, in fact, a discriminative model, as we were discussing before, where it would essentially try to maximize the conditional probability of the hidden states given the observations. Yeah?
So your goal was to detect if using of Walker would make it more or less likely to slip, right?
Yes, well, I guess the intermediate goal was to recognize activities. The ultimate goal, at least for our colleagues in kinesiology, was to obtain a simple automated way of compiling some results that would tell them which activities are more likely to trigger a fall. Yeah?
From the unsupervised perspective, what happens if you don't specify the numbers?
Yeah, so in the unsupervised case, if we don't specify the number of states, then the approach that I've mentioned here, well, does require us to give it a number of states. You would typically give it like an upper bound on what you think is the number of states, but then there are various techniques that can be used to also automatically discover the number of states. In fact, you can just use some form of cross-validation by varying the number of states and then seeing what is the number of states that gives you the best result on a validation set. Yeah? Okay, so I'm not sure I understood everything, but you're asking about the amount of data. So the amount of data that we had, if I just go back, it was essentially 8 experiments with 8 Walker users from Winston Park, and then 12 more that were essentially just older adults from the community who are not regular Walker users. So we essentially had 20 people who went through this walking course, and in each case it took somewhere between half an hour to 2 hours, depending on how fast they were. So this was the amount of data that we had. Yes, so okay, here obviously the amount of data needed depends on how complex is our model. So if we consider a recurrent neural network, and it also depends on how complex is the architecture of that recurrent neural network, then this might not be enough data. And therefore, yeah, it's not clear that it would necessarily perform better. So the observations tend to be not noisy, yes. So yeah, so here we account for this directly into the model here by having a distribution over the observations, right? So you see the sensor measurements are noisy, but that's okay because we have an emission distribution. For instance, if we use a Gaussian distribution, right, then it's clear that it allows the sensor measurements to vary and it accounts for the noise. Yeah?
Very generic question. So you said that you assume the same transition probability throughout the whole sequence for individuals, right? So how did you see any challenges? Because I'm assuming if, for example, the changer speed or the pattern of walking, that would affect the...
Yeah, very good point. So here, yeah, we do assume the same transition distribution for all users and across the entire experiment. And obviously, it would be better to do something that is tailored to each user. Now, in that work, we did not do this. I did do some other work that I don't have slides for at the moment, but where we did some form of transfer learning. So you could learn a general model for a population, but then after this, try to tailor the model to each user and then obtain even better performance. And then this can be quite effective because you're absolutely right that the way people walk can be quite different across different users, and this will improve the accuracy significantly. Okay, all right, let's keep going. Okay, so let's get into our second topic, so decision making in partially observable domains, and more specifically here we'll talk about planning and also learning whenever we've got partially observable Markov decision processes. Okay, so we're back to our picture for reinforcement learning. Now, again here, the main thing is that we do not have states, we have observations, but the goal is the same as in any other type of reinforcement learning, so we're going to choose actions that maximize the rewards. Okay, so when it comes to decision making, the underlying model for reinforcement learning is the Markov decision process, and I'm assuming that in some previous session this was covered to some extent. So I've got here just a quick picture to illustrate again what is a Markov decision process. So we've got our states that evolve over time. At every step, we choose an action that triggers a reward, and it influences the next state. Okay, now the problem with this picture is that here, this suggests that every action is chosen based on the previous state. Right? So normally in a Markov decision process, a policy is going to be a mapping from states to actions, but if we don't know the state, then we can't use that. So what are we going to do? Here, if we have observations, so the first thing is that we should augment our model to account for the observations. So let me introduce some new nodes that correspond to the observations, and then let me also change the dependencies for each action. So each action now can only depend on observations, not on the states, simply because they're not directly observable. And now, as you can see, this makes the picture more complex, more messy, and naturally is going to make our algorithms more complex too. Okay, in any case, this picture does account now properly for partial observability, and this is known as a partially observable Markov decision process. Okay, so POMDP, which is a common abbreviation for this, right, stands for partially observable Markov decision process, and that's what we've got in this picture here. Okay, so in terms of defining more formally what is a partially observable Markov decision process, we would typically specify all the following components. Okay, so we'll have states just like before, actions and rewards, but then we add observations. We also have a transition model just like before. Now we add an observation model too, just like in our hidden Markov model. We have a reward model, a discount factor, and then some planning horizon. So these are the typical components that need to be specified, and then we would find a policy that maximizes sum of rewards. Okay, so this is if we're given all of this, but in practice, we typically don't know all of these components, and then some of these things need to be learned as well, and this is where reinforcement learning kicks in. So if we're going to do reinforcement learning, what we typically work with are the observable things, so the observations. We know the actions we're going to choose. We get to observe the rewards that we receive, but now we don't know what the states are. We don't know what the transition model, the observation model, and perhaps not even the reward model, right? So these things are not necessarily known, and we're going to have to learn them, right? So reinforcement learning is this harder problem where we're trying to find a policy that maximizes expected rewards, but then only based on these things, where we're going to have to learn at least implicitly, maybe explicitly, about the missing components. Okay, so perhaps the simplest way to deal with partial observability in reinforcement learning is just to say, well, let's ignore the fact that our observations do not tell us about the state completely, and let's just treat the observations as if they are states. Right? So here this would mean that we can simplify the picture that I showed before, where every action could just depend on the previous observation, and let's just find a policy based on that. Right, so this is a common approximation, and perhaps the first thing you might want to try because it's simple. The obvious drawback is that if the observations are not informative enough, right, then you're missing on some information. You're not going to get a policy that's as good, and obviously we should be able to do better. In any case, that's a good start. Okay, so now, if we're trying to also learn about the model itself at the same time as planning, then in our reinforcement learning framework, this would mean that now our agent really has two components. There's one component where it's going to update the model, and then based on that model, then it's going to do some planning that will end up giving us a policy or a value function, and then based on this, choose an action. So here this picture is for model-based, partially observable reinforcement learning. I understand that the next session is going to be about model-based reinforcement learning, so we're probably going to see some of that again in the next session. But in any case, I need to introduce this simply because when we talk about partially observable Markov decision processes, we typically assume that we have a model. Okay, so yeah, so these are the two components, and now we're going to discuss how we can update our model, how we can do the planning, and also how we can do both of them simultaneously. Okay, so in terms of planning, what is common is in fact to say that instead of having an action that will depend on all the previous observations and actions, perhaps we could just synthesize all of that information into one item that we're going to call the history, or in some other cases we're going to call that a belief state. So here the information that's available to choose our next action is the history of past observations and actions. Now, using the inference technique that I explained earlier for hidden Markov models, then we can always try to compute a distribution over the current state given that history. And what is typical is to rename this and call it a belief state. So it indicates that this is our belief about what might be the underlying state. So then the question of inferring the underlying state can be called belief monitoring. And I've got, again, the same equation that we saw before for hidden Markov models. Now, the main difference is that I'm doing this in the context of decision making. So when I'm going to try to infer my hidden states, it depends obviously on the previous state and observation, but also the actions that I choose along the way. Okay, so this equation is the same as what we saw before, but now I condition my emission distribution on actions and my transition distribution on actions as well. Okay, so otherwise it's the same mathematically. Okay, so based on this now, there is a formulation for partially observable Markov decision processes and also reinforcement learning, where what we can do is simply replace the state by this belief state, this belief distribution. So we don't know what the state is. Normally, each action should depend on all the previous actions and observations, but then if I synthesize into my distribution over states what these previous observables are, then I might as well just create a node here that I'm going to call the belief state, and then I end up with a picture that is very similar to the picture for regular fully observable Markov decision processes, and therefore is easier to work with. Okay, so then this is one common approach to deal with partial observability, is that once we account for the fact that a state is not observable, then we simply replace the state by a distribution over states known as the belief state. Okay, any questions regarding this? Yes? Yes, okay, no, that was not intentional. So I should have B sub 0 and here B sub 1. So the idea is that I guess the distribution itself might be different at every time step. And then it's a distribution over a different random variable. So yeah, so I guess here I should have B sub 0, B sub 1, B sub 2, and so on. Yeah. Yes? That's right. So, okay, I guess what I explained here, yeah, let's go back to this slide, is that the belief changes in part as a result of actions, but then you're absolutely right that we don't have to perform actions. In some environments, the world evolves by itself. Like for instance, if let's say we're doing investment in the stock market, even if you don't invest, stock prices keep on changing, right? Same thing with the weather, it changes regardless of what you do. So here, I guess the fact that I condition on actions, think of it as simply that we're conditioning on actions if they are available. If they're not, then you could just remove it, or it's the same as not having any action. Okay. All right, so based on this now, we're ready to talk about how we can do planning and learning. And with this notion of belief, we can abstract out a lot of the challenges regarding partial observability. So for instance, we can do good old value iteration with a belief MDP, where I replace in the equations here, every place where I have a state, I replace that by a belief, and then so I'll end up with a value function that depends on beliefs instead of states. I'll have a reward that depends on beliefs instead of states, and then I can have a Bellman update here that also has every instance of state replaced by a belief. Okay, so we can have essentially the same type of algorithm value iteration that would typically be used in a fully observable Markov decision process, but now with respect to beliefs whenever it's partially observable. So at least conceptually, it doesn't have to be that much more difficult to deal with partial observability. Okay, so the key here again is that every time I've got a belief, what I'm really doing is taking an expectation with respect to the distribution over states that's encoded by my belief. So here you see the reward is really an expectation. The distribution over observation is also an expectation with respect to the belief. And then here this is my next belief based on the last action that I took and then the last observation that I received. So when I apply here Bellman's equation, right, then I take the sum of my current expected reward plus an expectation with respect to the observation times here the value for the next belief, where the next belief depends on what action and observation that I choose. Okay? But otherwise, it's really the same equation as before. Okay, so now that we understand this, when it comes to planning, there's lots of algorithms that one can consider. Yes, a question.
From the previous slide, is that reward function given, or are you doing one step look ahead with the state action pair to obtain a reward?
Okay, so yeah, so this algorithm, think of it as just an abstract algorithm that shows mathematically what we would do. And then now what I'm going to do is explain in more detail one specific algorithm to make this practical. Okay, because yeah, in terms of making this practical, there's obviously some challenges due to the fact that the beliefs are really distributions. So I cannot enumerate all possible distributions. I really have a continuous space. And then, yes, I'm doing here a one-step look ahead, but then I might not have these distributions available easily, so there's some challenges. But at least mathematically, this is what we're trying to compute. And now we're going to talk about some algorithms to approximate this. Yes? Oh, okay, that's a typo. So this should have been for all B. Yes. Okay, good catch. Yes. Yeah, so the observations are generally assumed to be noisy, and this gets reflected by this distribution here, right? So we're going to get some specific sensor measurements. These are concrete values, but then they might be off due to some noise, but then this gets taken into account by the fact that we've got a distribution as opposed to a specific value that we're expecting. Okay, so in terms of doing the value iteration that I explained briefly on the previous slide, then we need some algorithms that will take into account the intractability of computing value function, enumerating beliefs, and so on. And then, so there's been a lot of work in the past decades for this. We could classify these techniques between offline planning and online planning. So offline planning means that we've got our model let's say, that has been learned already. So let's say that I've already learned a hidden Markov model based on some data, and then that gives me the transition distribution, the emission distribution, it gives me everything that I need to construct a model. Then based on this, after this, I can simply find a good policy by using some of these techniques. This is here just a very short partial list of some of the work that has been done. And some of this work dates from many years ago, but obviously there's been advances since then. But in any case, I just wanted to acknowledge some of the pioneers in this work here. Now, more recently, the focus has switched on online planning, where instead of assuming that we've got a perfect model, because the reality is that we're going to be learning this from data, then we might as well just do planning with respect to the current belief, and then simply use a partial model to try to optimize what our next action is going to be. And this tends to be much more scalable, and the only drawback is that now we have to do a lot of computation between every action choice, but still with today's computational resources, this is often possible. So online planning, one very good approach that is scalable is to use Monte Carlo tree search. In fact, this was pioneered here by David Silver and his co-author here at the University of Alberta. So let me just explain to you briefly what the gist of this approach is. Okay, so if we're doing planning in a partially observable Markov decision process, then the simplest way to think about this is that we're essentially expanding a search tree. So we start with some belief, then we have a choice between some actions. So in this case, I only illustrate two possible actions, A1 and A2. Then after this, I would get an observation, and then this observation might occur, might lead us down to this belief or that belief with different probabilities. And then I end up into a new belief where, again, I'll have to choose the next action, come up with an observation, and then update, and then get yet another belief, and so on. So you could imagine that, you see, as we do the planning, we're essentially simulating all possible futures, and then if we don't worry about computational tractability, right, it leads to a search tree that grows exponentially in this form. Okay? Now, obviously, now the important question is, how do we make this tractable? So to make this tractable, there are three important ideas that are used by a lot of algorithms. So the first one is that at the leaf nodes, when I do this expansion of the search tree, I need to end up with some value based on some default policy. And what we could do is simply do some rollouts and take an average of those rollouts to end up with an approximate value for the leaves. Okay, so we're going to start at the bottom, compute some values for the leaves, and then we could simply do rollouts for some default policy, and that gives us an estimate. Okay, so that's the leaves. Now, in the tree that I showed, we have some chance nodes that correspond to the observations, and also some decision nodes that corresponds to the actions. The problem often is that the observations, there might be a lot of them, especially if we have continuous sensor measurements. So then one way to approximate this is to sample the observations based on our model, and it would lead to the following approximation. Okay, so here I'm going to sample some observations. So instead of considering all observations, I'm just going to consider a subset that are sampled, and then if I choose a subset that is representative and large enough, then that might be good enough. Okay. For the decision nodes, instead of looking at all possible actions and trying them all and evaluating them all properly, what we can do is simply expand the most promising actions. And this can be done simply by looking at what is our current estimate of the value for different actions, and then adding to this some exploration bonus. Okay, so this is based on an upper confidence bound that I believe you guys would have seen in the context of bandits. Okay, so here's the same idea. We're looking at different actions, and then instead of trying them all and evaluating them all accurately, we're going to only look at the most promising ones, and that means they should have a high value, and perhaps they should not have been explored too much. So this is here a bonus based on, I guess, the value that we expect to learn by exploring these actions. Okay, so when you combine these three ideas together, you end up with essentially the Monte Carlo tree search algorithm. So now let me just illustrate briefly with one picture how Monte Carlo tree search would work. I'm not going to do full justice really to the algorithm. I mean, this could be a 1-hour session just on Monte Carlo tree search. But if I explain it in one slide, the idea is that we have our search tree, right? And instead of being exponentially large, what we're going to do is expand it in a smart way, where initially we start at the current belief. We're going to select some nodes going down the tree, and each time we select some nodes, we're going to apply this equation here to always select the nodes that are the most promising. Then when we reach the bottom, we will always add one more node, so we're going to do an expansion. And then based on that node, after this, we're going to have to come up with a value for that node. So we're going to do some simulation, so some rollouts where we essentially execute a default policy and take an average of all the results that we obtain with this default policy. So this would correspond to this equation here. Okay? So that's where we execute our default policy. Once we get a value for that node, then we start to propagate back, so we update the values that we've got at all of those nodes according to this equation here. So this is just our approximation of Bellman's equation, essentially propagating back the values that we obtain. Okay, any questions regarding this? Okay, very good. So, one question, yes. Okay, so in this algorithm that I just explained, the transition distribution and observation distribution would have already been learned. Okay, so here I'm decomposing the learning problem and the planning problem. So if I just go back to this picture here, yeah. So you see, I'm going to have one part of my agent that's responsible for learning the model. And here the model that needs to be learned is really just an HMM. Right, so a hidden Markov model, and then I could do it in a supervised or unsupervised way as I explained before. Okay, so I would learn this, and once I have the model, then I would do planning to come up with action. So here what I just explained is essentially what goes in this box here. So how do we do the planning based on a model? Yeah?
Does the Monte Carlo research algorithm require action space to be discrete?
Yes, okay, the default Monte Carlo tree search algorithm indeed requires actions to be discrete. There have been some extensions to continuous actions as well, and I believe this is still an ongoing area of research too. Yes?
So how could I decide at which leaf node I should stop?
So how can you design a...
How
how do you decide at which leaf node you stop? So essentially in this picture that I have, what happens is that you start at the root, right? And then at every step, you select which edge to follow according to this equation. So that will tell you which node to go to next. But then at some point, you're going to select an action for which you don't have a node here. So then that tells you, okay, now you've reached essentially the bottom of your tree. And when I say the bottom, it doesn't mean literally a leaf in here. It could be a node somewhere in the middle, but for which we're missing some children. And then when you select an action that would not have a corresponding child, then this is where you would essentially create a new node. So it's based on this equation here that we would end up selecting where we stop and when we start expanding. Yeah? How can you perform Monte Carlo tree search when the action space is continuous? Okay, yeah, so when the action space is continuous, okay, one approach is that we're doing a maximization, right? So instead of doing a maximization where we would enumerate the actions, you could do the maximization by essentially doing continuous optimization, right? So you could consider a space of possible actions that is continuous, maybe over some interval, and then do this through continuous optimization, doing some form of gradient descent. This would be the simplest approach. But okay, I'm not entirely up to date on the state of the art for this. If you do a search in Google Scholar for, I guess, Monte Carlo research with continuous actions, you will come up with a few papers that deal precisely with this problem. Okay. Okay, so yeah, so this concludes what I wanted to talk about in terms of just the planning. But now, what about doing simultaneously learning and planning, right? So it depends on the scenario. So often in the industry, it's good to decompose things where you would have, let's say, part of your system that is just responsible for learning. You can double check how well it works and so on. And then another part of your system that's responsible for planning. And then you can also double check how good are the actions selected. So in the industry, this tends to be working well and often the preferred approach, at least in operations research. Historically, this is what a lot of people have done. Now, since we're going to be updating our model, sometimes even while we're planning, then it makes sense to actually do both of them simultaneously. And this is perhaps more elegant, at least from a reinforcement learning perspective. And so what I want to do is explain one approach for this, known as deep recurrent queue networks, that was proposed in 2016 by Hosnacht and Stone. And then in this case, what they did is they used a transition model that was a recurrent neural network, an observation model that was a convolutional neural net, and then for the value function, they use a deep neural network. Okay, so okay, just as a brief recap, I believe you guys have had a session on a recurrent neural network. So a recurrent neural net is a neural net where we have some connections that form cycles. We can always unroll this. And then one of the simplest type of recurrent neural network would in fact look very much like a hidden Markov model. And we can think of the recurrent neural network as a generalization of the hidden Markov model, where we don't necessarily represent the nodes as distributions. So they're not random variables. They're going to be vectors of values. And then the operations that we do are not necessarily linear. They could be nonlinear. They could be anything we wish. Okay, so a recurrent neural net can simulate and generalize an HMM, but then in its most simple form, it looks very much like what we've just talked about for hidden Markov models. So here we'd have hidden vectors that correspond to hidden states, and we'd have some inputs that correspond to our observations. Okay, in terms of recurrent neural nets, one type tends to be better to deal with long-range dependencies, which is the LSTM unit. So here I've got a picture of one variant of the LSTM unit. Now when you unroll this, you end up with essentially, again, a network that looks very much like a hidden Markov model. The main difference is that with the LSTM units, we're going to introduce gates that will determine how information flows. So when does information go from one node to another, and when should it not? So if I introduce some gates in the LSTM network, I would have, let's say, an input gate that determines whether the input will influence the hidden vector. There's a forget gate that will tell us whether we carry information from before into our new hidden vector. And then there's an output gate that will determine whether we produce an output or not. Okay, so that's the main contribution of the LSTM unit, and then all of these gates would essentially depend on the input and then the previous hidden vector. So at least in one variant of the LSTM network, right, this is what we would obtain, and you can think of it again as a generalization of the hidden Markov model. Okay, so this deep recurrent Q network that was proposed, it was designed specifically to deal with partial observability. So historically, in reinforcement learning, when people were applying techniques on Atari games, then you would feed in, let's say, one frame, or otherwise a short set of frames, like maybe up to 4 frames, and then treat this as your state. The problem is that in some games, there might be information that goes back further than just the last 4 frames, and then you need to have a technique that can remember some of that information, and then the recurrent neural networks provides us with a way of doing this. So the idea is that every frame is going to be fed into a convolutional neural net that more or less corresponds to the emission distribution of a hidden Markov model. And then it will update our hidden representation in the LSTM network here. So there's an LSTM network that goes horizontally here that carries information over time. And then this gets fed into another network that computes Q values. Okay? So this is one modern technique to deal with partial observability that uses different types of networks and more or less mimics what we've seen so far with hidden Markov models. Yes?
So in this model, were the transitions between hidden states probabilistic or deterministic?
Okay, so in this work, I believe everything is assumed to be deterministic. Now, that being said, when I say it's deterministic, is that you can assume that the transition model is going to be deterministic, and for video games, chances are it is mostly deterministic. Now, what we could do as well is say that what we're representing with these different vectors could be essentially just the powers of some distribution. So even though the computation is deterministic, it could correspond to encoding implicitly some update about some distributions, and then even though everything is deterministic here, would just mean that the update of some distribution is deterministic. So we could still capture stochasticity with this approach. Yeah? Yes, that's right. So, yeah, okay, I was going to talk about this in the results, but since you're bringing it up, you're right that here, to induce partial observability, they changed the way the simulator was working in order to essentially black out some of the frames as if we could not observe every single frame, and then that forces the network to try to infer what it's missing. So if the frames are really a good approximation of the states, but now you cannot observe some of them, that induces partial observability. So they did this here for the sake of the experiments. Obviously in practice, you don't need to do that. And here really, they should have considered some scenarios where there is some natural partial observability. Yeah?
Just the fact that you don't have access to that trajectory of changing the frames, isn't that already a partial observation? Because, for example, we concatenate like 4 frames for DQ1, so that like we assume this gives us enough information about the direction of the movement, but it can be better if we have like 10 or more. So isn't this already, I mean, is it because of the frame or not partial
Yeah, so okay, yeah, typically in previous work, people would only consider the last 4 frames, and then they would assume that all the information that's needed is in those 4 frames. But you're absolutely right that here, maybe we need to look back 10, 12, 20 frames, and then that information would be missing, and here they can still, at least in theory, capture some of that information through the recurrent neural network. So it is addressing that. It's just that, at least empirically, in the context of a Atari game, most games, it is indeed sufficient to just consider the last 4 frames. Okay? So if we look at the results here, they have some games, and then this is their technique, deep recurrent queue network. They just compare it to a regular deep queue network that would consider only the last 4 frames. It would just have a convolutional neural net, so no recurrent neural net. And then on most games, right, then the results are more or less the same. However, there are 2 games, I guess Double Dunk and Frostbite, where they obtain significantly better results, because in those games, indeed, it was useful to look and consider some of the previous frames. And then in addition, they were also blacking out some of the frames in the last 4, so to induce more partial observability. Okay. All right, so according to the counter here, I've got no more time. So I do have one last topic, so I'm not sure if I should stop here. What do you guys say? Should I stop here?
Yeah, probably.
Okay, or should we take a vote from the audience?
How long do you have?
I can try to go faster, like maybe another 10 minutes. Okay, I think the crowd voted. Okay, so let's talk about Bayesian optimal exploration. Okay, so when it comes to reinforcement learning, an important challenge is the exploration-exploitation trade-off, right? And then this, there have been a lot of work on this. What I'm going to talk about is one specific line of work known as Bayesian reinforcement learning that comes up with a nice principled way of dealing with this exploration-exploitation trade-off. So the benefits are that we're going to have a balanced way well, actually a Bayes optimal way of trading off exploration and exploitation. In the context of model-based reinforcement learning, it will help us to mitigate model bias, and then it will also reduce our data needs. The drawback is that computation is going to be more complex. Okay, so here the idea is that if we consider traditional reinforcement learning, then we would have states, action, rewards. Here I'm going to assume for this section that states are directly observable. Okay, so we could also consider states that are not directly observable, but for the purpose of just focusing on the exploration-exploitation trade-off, let's just keep things simple, and I'm going to assume that states are directly observable. Okay, so what's missing in reinforcement learning is that we don't know our model. So here I'm going to put together the transition model, the reward model, all into one model. So it's a distribution over both rewards and states, given the previous state and action. Now it turns out that we can model reinforcement learning as a partially observable Markov decision process, which is going to lead naturally to a form of Bayesian reinforcement learning. So here you see in this model, the traditional model, what we're saying is that we don't know what is the underlying model. Okay, and if we don't know what it is a bit the same as saying that we're missing some information and perhaps we need to learn about this, perhaps express a distribution over that, and maybe we could treat that as a form of hidden state. So if we view it this way, it leads us to a form of reinforcement learning that we can represent as a POMDP. So here, what I'm going to do is augment my notion of state to correspond to what I would call information states. So I'm going to have both my physical states and then some parameters of my model. Okay? So in reinforcement learning, we don't know what the model is because we're missing the parameters. Normally we need to learn these things. I can push them into my state definition to obtain an information state, and then the rest stays the same. So I'm going to have actions, I'm going to have rewards. But now, once I've pushed into my information state these parameters, then interestingly, I obtain a model that is known, because if I can condition on the parameters of my model, then my model is known. So here I will know what is the distribution over R and S prime as long as I know what theta is. It's just that now, you see, I include theta as part of my state definition. So I can formulate reinforcement learning as a POMDP. And now what it means is that I will instead look for policies that are mappings from states and histories to actions, or otherwise Q functions that are going to be mappings from states and histories and actions to real values. Okay, so this is the main distinction. So traditional reinforcement learning, policies are mapping from states to actions. The problem is that we don't know really how to deal with the fact that we're missing some information about our model, and then we don't condition on that. But now if we explicitly condition on that, then we obtain a different type of policy, and it's going to be a policy that is richer and perhaps can deal with the exploration and exploitation trade-off in a more principled way. Okay, so the problem with formulating this as a POMDP is that all I've really done is push into my state definition the parameters. So I don't know my model. Now I made my model known, but instead I made part of my state definition unknown. Okay, so it's partially observable. So it's not clear that we're gaining anything by doing this, but if we do one more transformation, instead view reinforcement learning as a belief MDP. So here what I could do is say that my state is going to be the physical state with a belief over my model parameters. Then I obtain a state definition that's rich again. The difference is that now belief states are something that we compute according to Bayes' theorem, according to the update formula that we discussed earlier. So we know what that is, and it's not unknown anymore, so it's known. So we know how to obtain these things. Okay? And then the model again will be known. So now what's interesting is that we can rewrite reinforcement learning as a pure planning problem from a Bayesian perspective, and now everything is known. So the goal will still be the same, to find a policy or a Q value. And then the difference is that now we're going to condition on the physical state and also what is our belief about the underlying model. So B here stands for belief space, right? So it's a distribution over the parameters of our model. Okay, so in Bayesian reinforcement learning, just to clarify why these things are known, here you see if I want to express my model as a distribution and claim that this distribution is known, then I can factor it as a distribution for the physical model as well as my belief model. For the physical model, this is the equation that I would use where I integrate out my unknown parameters, and that's the trick that allows me to treat this as known. So it's the fact that I'm going to integrate out with respect to my belief. And now for the belief update, this is the belief monitoring equation that we've seen before. It turns out that it's not really a distribution. It's going to be something deterministic, and then it's just the distribution over the parameters based on the information that I've seen so far. Okay? So that's how I'm going to formulate things. Any questions regarding this? Okay. Yes, one question.
How practical is it to integrate over all possible parameters in this particular integration?
Okay, so to integrate over all possible parameters is indeed one of the challenges. So here, in some cases, like discrete states, simple model, we can do this in closed form. More generally, we can use particle filtering that I explained before. And now the modern approach today would be to use a Bayesian neural network to do that, okay, where we can approximate as well through sampling. Okay, so I'm going to skip a few slides in the interest of time. So this was an example to show how we can do some of these computations in closed form. And let me go straight to the following. So now let's say that I want to do the planning and the learning. Since I've now shown that I can formulate reinforcement learning as a pure planning problem where everything is known, then it means that I could use some form of value iteration or policy iteration, and then after that simply execute my policy using this algorithm. Okay, so we can do this. The main question is simply, how will I find my policy pi star or my value function v star? And then, so there are various approximations that can be used for that. Okay, so let me skip a few more slides and go straight to one algorithm here. So PILCO is an algorithm that is essentially a model-based Bayesian actor critique that exploits this framework that we've just discussed and has achieved some really good results on a number of problems. Okay, so PILCO essentially consists of this pseudocode where the idea is that at every step into this loop, we're going to evaluate our current policy using a critique. Then we're going to update it using an actor, and then simply execute, and then update our belief based on the information that we receive. Okay? So the beauty is that this can be done without interaction with the environment because we're planning. We do not need to worry about model bias because we're going to take into account uncertainty through the various distributions. The main complexities in terms of representing the policy and the value function, but then this is where we can leverage the power of deep neural networks to get some good approximations. And then so PILCO was in fact proposed in 2011 based on Gaussian processes, and then there's a more modern version of it in 2016 that uses Bayesian neural networks to achieve more or less the same thing. The algorithm was quite good at reducing the amount of data that is needed because it does perform the exploration in a way that is Bayes optimal. And then the algorithm here, we can see the amount of interaction with the environment that was needed on one task. So I believe this was the inverted pendulum task. So it tends to be a lot less than any of the other techniques. And then this is thanks to the fact that we are representing information about what we know and don't know through a distribution. And then we can do some planning offline so we can optimize well our policy before we start acting and also between every action. So in terms of obtaining something that is data efficient, then the Bayesian approach is quite effective for that purpose. Okay, so let me conclude here. So I talked about three things: belief monitoring based on HMMs and RNNs, also how to do decision making with partially observable reinforcement learning. And then the last topic, even though I did not go into a lot of details, but you guys can look at the slides later on, and I'm happy to answer questions too, is Bayesian reinforcement learning, which I think is quite promising in terms of reducing data needs. Now, if some of you are interested in other topics, some other directions that I think can be quite exciting are to look at robust reinforcement learning, self-supervised reinforcement learning, constrained reinforcement learning, object-oriented reinforcement learning, and also mean field reinforcement learning. Okay, let's stop here.